So today we're lucky to have Paul Smolinski here to give a presentation for us. Paul is a professor of cognitive science at Johns Hopkins and also a partner researcher in the deep learning team here in MSR-AI. So as such, he's sort of perfectly suited to give us this nice overview of sort of the history of thoughts of human cognition and approaches, and how the pendulum has kind of moved between symbolic and neural and back and forth. And I know his current work is on looking at how you can merge them to create these neural symbolic approaches that hopefully take the best of both worlds. And I assume we'll learn a bit more of that as well. But with that said, Paul, why don't you go ahead and take it away? And you're muted right now.
Are you seeing my screen, Matt?
Yep, we can see your screen and hear you.
Okay, thanks a lot. Let's get started then. Okay, so in the beginning, models of intelligence use representations that were discrete symbol structures and manipulated them with discrete rewrite rules, like those of logic or grammar. But this wasn't invented in the 20th century. It was invented around 400 BCE, as we'll see soon. But anyway, in the mid-1980s, the field took a huge swing. The parallel distributed processing group, among others, showed how numerical vectors listing the activation values of groups of model neurons could be used as powerful ways of representing information for intelligent processing. The 1990s saw another swing back to symbolic representations, which were now assigned probabilities rather than manipulated by rules. In the 2000s, this pendulum swung again back to numerical vector representations designed from data by deep learning. So what's going on here? Why can't the field make up its mind on such a fundamental distinction between using symbolic computation or neural computation? To resolve this, I propose we follow advice from my mother, who used to say, allegedly quoting Yogi Berra, when you get to the fork in the road, take it. Clearly, both types of computation are essential, and this is the moral of these lectures. The pendulum will finally stop swinging only when the field wises up and adopts neurosymbolic computation. So to really understand what's going on here, I think we need to take a historical perspective. AI inherits much of its intellectual technology from centuries of the study of human intelligence, which in the recent era goes by the name cognitive science. Cognitive science, in turn, inherits much of its intellectual technology from computer science by adopting the view that what we have in our heads is really a computer. But what type of computer do we have in our heads? One built with symbolic computation or neural computation? In this and next week's presentations, I'm not wearing my MSR-AI researcher hat, but my professor of cog-sci hat. When I told Henry Kudgerman about my favorite course, Foundations of Cognitive Science, he asked if I'd consider giving a 2-hour synopsis of it here. Unfortunately, the course is entirely based on class discussion of over 30 readings, and there are no lectures. So I've created these lectures just for the occasion, and they have not been field tested. So please be kind and keep in mind that I'm trying to compress 32 hours of class time into 2 hours. This requires oversimplifying and skipping lightly over many deep and complex issues. So please bear with me and take these lectures as a view of this complex material from outer space. It would be helpful if you submitted your questions by chat or held them to the question period. Now, before proceeding, I want to emphasize that the history of cognitive science, or of AI, is not for me a field of research or expertise. My goal here is only to put a lot of ideas on the table for all of us, especially interns new to the field, to think about and perhaps go investigate later in some detail. I'll raise a lot of questions, give a lot of proposed answers, but not favor any particular answers, except maybe at the very end next week. So why do I think it is crucial to develop neurosymbolic architectures for AI? To get started in the cognitive science perspective on this question, let's start with a very concrete case study. learning word formation, specifically the English past tense and the German plural. Debates about this in Cog Sci have been raging on and off since the birth of the field and continue to this day. The most recent round playing out in ACL. For a 2018 paper in the Transactions of the Association for Computational Linguistics, Chris Kirov and Ryan Cotterill built a modern-day LSTM sequence-to-sequence model to map an English verb stem to its past tense form. This includes regular verbs like pick and pig and pit. Now, the past tense of all these is written ed, but pronounced in 3 different ways, as shown here: picked, pigged, pitted. The task also includes irregular verbs that don't follow these rules, like come goes to came. Kirov and Cotterill argued that their model provides a good account of human performance on this task, succeeding where first-generation models failed at correctly producing irregular past tenses. But then at ACL 2019, Maria Corkery, Yevgen Matsuvevich, and Sharon Goldwater argued that, well, actually, it doesn't. For made-up words, production probabilities of alternative past tense forms do not correlate well with humans. Just this month, Kate McCarthy, Goldwater, and Adam Lopez built a corresponding model of the German plural and argued that it too failed to learn like humans. Now, this debate dates back to at least the 1960s, when Susan Irvin documented that children first successfully produced came, but then started to say comed. She argued that because they've never heard comed, they must have generated it. Clearly, they learned the regular rule and were now mistakenly applying it to come. In this era, learning language meant learning rules. But one of the forces that swung the pendulum over to neural representations was a chapter in what became the Bible of a new generation of neural network modelers, the PDP books. Dave Rumelhart and Jay McClelland argued that a simple neural network model shows the same learning trajectory as kids, even though it is obviously not learning any symbolic linguistic rules. Now, language learning became learning the statistics of data from the training environment. In a legendary reply, Steven Pinker and Alan Prince argued that the PDP neural model suffered from a dozen serious flaws that could all be blamed specifically on the absence of symbolic representations and rules. They advocated a dual root view in which kids have one system that learns a symbolic rule for the regular cases and a separate neural network system for the exceptions. Another player in this debate was Gary Marcus, who you may know as a contemporary critic of deep learning. Well, Marcus's career began with this follow-up study with Pinker and others, arguing that the only reason the PDP model could learn anything even remotely resembling the regular past tense rule of English is that it is an extremely frequent pattern. Where the regular rule is very infrequent, as they argued was true for the German plural, PDP models would have no hope of success. This year's ACL paper by McCarthy et al. Essentially argues that Marcus, Pinker, and colleagues were right, not just about 1980s PDP models, but even 2020 deep learning models. The debate over whether language learning meant learning symbolic rules or learning statistics of the training data raged vigorously for years. Here are 14 examples of some of the subsequent modeling papers addressing this debate. Now, from the very concrete case of the English past tense, let's zoom way out on the debate over whether human cognition is symbolic or neural computation, and take advantage of a very helpful geographic metaphor here that was illustrated in a figure in a paper of Dan Dennett's, which I've augmented a bit. At the center of this plot is the eminent philosopher Jerry Fodor, who, when at MIT, called all approaches to cognitive science West Coast, except those at MIT, which form the East Pole. Every direction away from MIT goes west. The East Pole view is anchored in philosophy by Fodor, in linguistics by Noam Chomsky, and in psychology by Liz Spelke and Sue Carey and Steven Pinker, all having spent key parts of their careers at MIT. The East Pole is quite unified, well-defined, and coherent. We'll start by focusing on this view. In contrast, spread around the West Coast and filling in the Midwest are a huge variety of views that have nothing in common except that they all disagree with the East Pole, each in a different way. Time permitting, I'll mention the green names I've added, as well as 10 of Bennett's originals in black. By the way, there's still a correlation between holding East Pole views and actually working in the eastern US, but the geography here is intended to be purely metaphorical. In this slide, I'm going to give a crude timeline of some of the key developments, most of which I'll be explaining shortly. Please bear with me as I run through this quickly. The East Pole view in linguistics was articulated by Chomsky in the 60s and then experimentally supported by psychologists. The authors shown in red on this slide will be briefly discussed in the story I'll be telling in these lectures. For his views on the cognitive universality of grammar, Chomsky credited the work of the Port Royal grammarians in France 3 centuries earlier. He called his approach Cartesian linguistics because of its roots in the work of René Descartes. We will start the story of this so-called rationalist tradition with the work of Plato in Greece 2,000 years earlier. But as we're about to see, rationalist thought was not just a Western construct, and although I unfortunately won't discuss them much, I just wanted to mention important non-European traditions too. Now, while Chomsky's own work focused on syntax, his work with Morris Halley founded the modern era of phonology, the grammar of sound structure in language. I mention this because this approach was in fact pioneered in ancient India by Panini. Panini's formal rule-based grammar of classical Sanskrit is still regarded by many as the most complete generative grammar ever developed. Meanwhile, in the AI sector of the East Pole, John McCarthy's logic school of AI was the culmination of millennia of formal work on logic, including many important developments such as the Port Royal logic and even Panini's logic, which he developed for his grammatical work. Other non-Western founders of formal logic in the ancient world included Gautama in India and Motzi in China. Back in Greece, hugely influential in the West for his work on logic, but also many other areas, was Plato's student Aristotle, whose views became undeniable truths in Europe for nearly 2,000 years. Likewise, the roots of many West Coast views go back centuries as well. The PDP approach to neural models of intelligence, also known as connectionism, follows philosophical empiricism developed in the 17th century by the British empiricists, such as John Locke and David Hume. Connectionism also draws from more recent work in neuroscience, especially the work of Donald Hebb in the 1950s. Opposed to Chomsky linguistics, cognitive linguistics draws from the experimental cognitive psychologists' work, such as that of Eleanor Rosch. Cognitive psychology was itself a reaction against another West Coast view, behaviorism, in which B.F. Skinner claimed that human cognition, even language, could be explained using the concepts he developed to explain the behavior of pigeons in simple conditioning experiments. Finally, we zoom out in cognitive theory space, which is defined by many dimensions along which theories differ. We just implicitly discussed one dimension. Does the theory follow the empiricist view that all knowledge derives from experience, or the rationalist view that much of our most important knowledge is prior to experience, innate? Here are other important distinctions. Today, I'll quickly discuss several of those in green. Now, these are all distinctions pertaining to cognition itself. There are also important distinctions about how cognitive science should be practiced. These are issues in the philosophy of science, including these 8 or so issues. Now, the plan for these lectures is to take up these issues in sequence. As you can see, as always, I've packed in more material than anyone can absorb in 1 hour. You may want to tune in and out a bit to conserve attention for the parts that most interest you. Okay, we'll start now with perhaps the most fundamental issue, this one. What is cognitive science the science of? Brain dynamics, or behavior, or mental knowledge? The East Pole position here is emphatic. Even though it is brain dynamics and behavior that are measurable, cognitive science should be the study of mental knowledge, which is not directly observable through sensory perception. To understand this somewhat paradoxical position, we need to view it from the perspective of rationalism. Plato emphasized that perception cannot provide knowledge. Plato's scorn for experience is a preview of Chomsky's rejection of corpus data for studying language. Why can perception not provide knowledge? Well, consider that having exactly equal length is a concept we know, yet we can never perceive this sensorially. More generally, the most certain knowledge we have is about what we can't perceive, mathematics. In his famous parable of the cave, Plato asks us to imagine a group of prisoners chained for life so that all they have ever seen is the wall of the cave in front of them, or they see their shadows cast by the fire behind them. They believe the shadows are the reality of their world, although we know they are merely images projected by the real objects. Plato says that our own perceptual world is likewise not reality, but merely the shadows cast upon us by the reality that he calls the world of ideas. Since knowledge cannot arise from perception, it has to come from somewhere else, and Plato posits that it comes from recollection, from past lives. Now, this is pretty untenable, but it does anticipate Chomsky's view that our deepest knowledge of language is innate, not learned from experience. Plato also believed that the true student of astronomy is not to be troubled too much about the actual heavenly bodies, but with the mathematics of the motion of ideal heavenly bodies, foreshadowing Chomsky's notion of linguistic competence, which cannot be observed in language behavior. Fast forwarding 2,000 years, the preeminent rationalist René Descartes, who philosophers call the founder of modern philosophy, argued that the only thing whose existence we can be certain of is our own mind. All else can be doubted. Perhaps what we think is real outside our heads is just a dream, or perception deceived by an evil demon, like the Matrix. A central pillar of rationalism is that what's outside our heads is a poor cousin of what's inside our heads. For our second key dimension of theory space, we ask, should cognitive science seek theories that explain the details of actual human performance, or theories of competence, the knowledge underlying performance, ignoring the vagaries of particular instances of use of this knowledge? As we already saw anticipated in this remark of Plato, the East Pole position is that we need to find out what the underlying knowledge is first. Only then can we study how the knowledge is acquired by learning algorithms and used by processing algorithms. Now, in the case of language, this was Chomsky's position, of course. How did it actually play out for Chomsky? Well, Chomsky says that knowledge of language competence, that is, consists primarily of two things. First, the mind's ability to construct representations of linguistic expressions like sentences or words, symbol structures like these. I hope you'll forgive my laziness in using my whiteboard drawings from class. On the left is the parse tree of the noun phrase, the man who I think that you said that you had seen. The arrows show movements of symbols between positions. On the right is the mental representation of the noun phrase, the man who I wonder which scone preferred. The second component of competence is knowing principles that determine which structures are well formed. These principles define the grammar. For example, one such principle is subjacency, which says that each step of movement may not cross more than one bounding node. The set of bounding nodes is a parameter in this principle. Here's how this parameter explains cross-linguistic differences. As you will have noticed, the structure on the right, the man who I wonder which scone preferred, is not acceptable English, marked conventionally by a star. This is because, on the Chomskyan view, the set of bounding nodes in English includes the S sentence node, and this step of movement here crosses one and then a second S node, violating the principle. Now, astonishingly, the Italian version of the same phrase is acceptable. Why? Because the parameter has a different setting in Italian. S is not a bounding node. In Italian, S prime is. This is the only S prime node here that's crossed by this movement, so it does not violate the principle in Italian the way it does in English. In Chomsky's view, knowledge of principles is innate. These principles structure how children analyze their linguistic input. They know they need to observe which nodes can be crossed by movement in their language, so they can learn the value of the parameter, the set of bounding nodes for their particular language. We'll come back to this in a moment when discussing Immanuel Kant's reconciliation of nativism and empiricism. So as we just saw for Chomsky, the data of language are expressions labeled as well-formed or ill-formed. The task of the linguist, generative grammarian, is to logically derive the labels of expressions from the principles. These are theorems that require symbolic proof. What is the state of the art on this task, you might ask? Well, it's provided by theories from theoretical linguistics and models from classic symbolic computational linguistics, not by neural models, whether they be NLP or connectionist cognitive models. These models do not perform this task. They do not symbolically deduce the data from principles or axioms of a theory. They are categorically banned from the leaderboard. Could neural nets possibly have innate knowledge of principles of universal grammar such as subjacency? Well, as it happens at the Cognitive Science Society conference this week, Tom McCoy, currently an MSR summer intern and the curator of questions during this very talk, will show how this can be done through meta-learning. Now we're ready for another big dimension of cognitive theory space. Is the mind primarily a device for processing highly structured symbolic information or for performing statistical analysis of experience? As we just saw in Chomsky's work, the East Pole position is that the mind is principally a symbolic structure processor. For this issue, too, the East Pole roots lie in antiquity. Aristotle was a founder of deductive logic in the West. One of his syllogisms asserts, for example, that if we know that some A's are B's and that all B's are C's, then we can deduce that some A's are C's. The point is that the content of A, B, and C, what they mean, is irrelevant. Only the structure of this information matters. This is pure meaning-free symbol manipulation 2,000 years ago. And even before Aristotle, in India, Karnani used pure symbol manipulation to do the task of generative grammar that we saw on the previous slide. Opposed to the East Pole are West Coast approaches that take statistical analysis as the primary computation in cognition. The historical roots of this view date back to the British empiricists, as I've already mentioned. The empiricist emphasis on statistical computation derives from their position on the origin of knowledge. Whereas the rationalist focus on knowledge generated internally, empiricists, including many West Coast approaches, take the view that all knowledge is extracted from the external world through experience. John Locke maintained that all knowledge starts from perception and is built up by associating together sensations that are similar in their content or in their time of perception. The empiricists did an amazing PR job and convinced the entire English-speaking world of their view. Now in our community, there is virtually universal acceptance of the view that our minds start as blank slates. You see it all the time in AI papers, stated with absolutely no evidence. It's obviously true, just common sense. But there are grave problems with this, actually, and here are just two. That our perceptions are caused by events outside our heads. We can't perceive outside events causing our perceptions, so we can't know that they do if all knowledge derives from perceptions. So we're back to Descartes and the problem of the matrix. Second, can we justify the belief that past correlations predict future ones? What good is it to know that past correlations are if they don't inform us about the future? But the only evidence we have is that in the past correlations predicted what were then future ones. But that's all in the past. We can't justify believing that what is now in our future will be statistically like the past. Of course, inference to future predictions is uncertain, but there's simply no basis for even that form of inference that can be extracted from experience alone. These are unsolvable problems for empiricism. And in fact, the great empiricist David Hume himself just gave up on causation, concluding that there is only correlation, and our minds just have a habit of thinking that A causes B when the correlations between them are right. Now, as we've seen, the East Pole position, on the contrary, is that much crucial knowledge is not extracted from experience. Chomskyan innate knowledge of linguistic principles was anticipated by Plato's conclusion that knowledge must arise from recollection, since it can't arise from experience. Aristotle's syllogisms enables new belief to be rationally generated internally to the mind, no external input needed. Although this form of knowledge is purely tautological, essentially true by definition. Immanuel Kant provided a synthesis of empiricism and rationalism, which I think comes closest to the right view in cognitive science today, that we are born with some important innate knowledge for how to impose organization on our experience, so we can best learn from it. For Kant, this included innate knowledge of a four-dimensional Euclidean world, which allows us to organize our perception of objects and events. Innate knowledge that causal relations exist among external events, and innate knowledge that our perceptions are caused by external events. For Chomsky, recall how innate knowledge of the subjacency principle allows children to organize their linguistic experience so as to be able to learn the specific parameter values characteristic of their particular language. This is very much the way Kant saw innate knowledge interacting with experience. The study of innate knowledge is now highly experimental, actually. The field of cognitive development was revolutionized in the 1960s by methods for inferring knowledge inside infants' heads by measuring the time they spent looking at different types of events. Up to 6-month-old babies distinguish between event relations that we consider causal and those we consider merely correlational. They respond differently if one object is set in motion upon collision with another. If you can see my hands, they respond differently to events like this than when an event is set into motion by another object that comes close and stops without making contact, like this. The correlational structure is exactly the same, but one we regard as causal and the other not, and infants make the same distinction among events, at least by the age of 4 months. These methods have also revolutionized the study of animal cognition, and there the study of innate knowledge is informative about knowledge that evolution might have provided humans. Delphi summarized her extremely influential theory of core knowledge systems this way. This research suggests that the human mind is not a single general purpose device that adapts itself to whatever structures and challenges the environment affords. Humans learn some things readily and others with greater difficulty by exercising more specific cognitive systems with signature properties and limits. The human mind also does not appear to be a massively modular collection of hundreds or thousands of special purpose cognitive devices. Rather, the mind appears to be built on a small number of core systems. These systems are knowledge of inanimate objects and their mechanical interactions, knowledge of animate agents and their goal-directed actions, knowledge about sets and their numerical relationships of ordering, addition, and subtraction, knowledge about places in the spatial layout and their geometric relationships, and finally, knowledge for identifying and reasoning about potential social partners and social group members. No matter how you look at it, this work presents a major challenge to contemporary AI based on deep learning and neural networks. Either such abstract knowledge systems are innate, or they are learnable, unsupervised, from the infinitesimal quantity of input that infants received compared to the gargantuan training sets that are now required by deep learning. What AI needs to do, argues Gary Marcus, is to abandon empiricism and study the proper use of innate knowledge, like that which makes the highly data-efficient learning of infants possible. On the other side, there's an important challenge too, and a challenge to the East Pole view that comes from a surprising place. We return to our first issue, what is cognitive science the science of, and now consider the second option, behavior. Behaviorism is a West Coast perspective that dominated experimental psychology in the US for the first half of the 20th century. Strangely, it has in fact made a comeback with a strong presence in contemporary neuroscience. B.F. Skinner argued that psychology should be the study of behavior and that we should explain behavior from the history of positive and negative reinforcement experienced by the subject. On the other side, nearly all of modern cognitive science says behavior should be explained by inner causes, states of the mind, beliefs, goals, and so on. But Skinner argued that explanation by inner causes has three fatal flaws. First, it is unnecessary. If inner states are lawfully determined by reinforcement history and behavior is lawfully determined by inner states, then behavior is lawfully determined by reinforcement alone. We can just cut out the middleman, inner causes. Second, explanation by inner causes is unfalsifiable, fatal for any science, because inner causes are not observable. And third, explanation by inner causes is circular. How does it explain why a horse is drinking? Because of the inner cause of thirst. How do we know the horse is thirsty? Because it is drinking. Completely useless circular reasoning. Now, I think these are serious accusations to which cognitive science must have very secure defenses. My own, in a nutshell, goes like this. Hypothesizing inner causes is necessary if steps 1 and 2 of Skinner's argument are intractably common, and valid if the number of hypothesized causes is small relative to the number of observable predictions that they make. This can be formalized, I think, in computational learning theory's version of Occam's razor. When the dimension of the hypothesis space is much smaller than the number of observations, the probability of correct generalization to unseen examples can be good. Now, Skinner's approach to explaining language, what he called verbal behavior, extended his philosophy from pigeons to people. Then Skinner wrote a book in 1959 extending this to verbal behavior, which was followed rapidly by a review written by Chomsky, in which he granted that behaviorism had proved successful for explaining simple behavior of simple organisms, but that for human language, what Skinner was doing was just play acting in science, that behaviorist descriptions are merely vague paraphrases of precise, formalizable mentalist descriptions of inner causes. Publication of this review was one of the events that launched him to the status of a superstar, and in fact to many, even a god. Chomsky's sarcastic, condescending tone in this review would characterize his style throughout his career. Now, for this reason, within much of cognitive science, reinforcement learning does not have a good pedigree. Now we shall take up an issue that is central to cognitive science across the board. Should a cognitive theory be a computational theory, viewing the mind as a machine that takes data in, processes it according to an algorithm, and outputs behavior? On this issue, nearly all cognitive scientists agree that the answer is yes, although we'll see a little bit of exception in next week's discussion. One of the earliest modern expressions of this view was Alan Turing's classic 1950 paper. At the end of the paper, like many AI writers that followed him, he described an approach to AI based on learning from a blank slate, simply asserting that is how children learn. Instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? Presumably, the child brain is something like a notebook as one buys it from the stationers, a rather little mechanism and lots of blank sheets. He then again, with no justification, asserts that learning in children is reinforcement learning. We normally associate punishments and rewards with the teaching process. But putting these aside, the important point of the paper for our story is really about something else. The paper is really about the question, can machines think? He asserts that the question is too meaningless to take seriously, so he proposes to replace it with what he calls the imitation game, which has become what we now know as the Turing test. Turing also began the tradition of absurdly naive, over-optimistic predictions about AI. I believe in about 50 years' time, it will be possible to program computers with a storage capacity of 1 megabyte to make them play the imitation game so well that an average interrogator will not have more than 70% chance of making the right identification after 5 minutes of questioning. The Turing test has, of course, been enormously influential and widely accepted within AI, but from the perspective of cognitive science, it is seriously defective. It is entirely behaviorist, appropriate for 1950. It reduces intelligence to behavior, ignoring entirely what goes on inside the system. It replaces a scientific search for a theory of intelligence with the judgment of an informed, naive human observer. Does this system's behavior seem intelligent to you? Here's an analogy from physics. Suppose we said, the question, is an object hot, is too meaningless to take seriously. We should put the object in a closed box, let an observer reach in and touch the object, and ask the observer, does this seem hot to you? Of course, that's ridiculous. We'd never do that for a physical science, the way Turing proposes to do it for a science of the mind. Physics gives a theory of temperature with techniques for quantifying the hotness of an object, laws that govern temperature, and ultimately reducing being hot to a deep internal property of the object, the average kinetic energy of the molecules that make it up. So Turing essentially dismisses entirely the possibility of a science of intelligence. This is absolutely not the case for computer scientists who followed him. The founders of AI took their job to be to characterize the internal computational properties that make a system intelligent. First, we'll take up the work of John McCarthy, and then look at the work of Newell and Simon. These authors occupy a central place at the East Pole. But before we discuss these East Pole AI pioneers, let me point out how contemporary deep learning is a return to Turing's West Coast behaviorism. Turing's behaviorist stance, refusing to look inside the system, is evident in contemporary AI because of the difficulty of looking inside neural networks. Concepts from cognitive science about system internal properties are now, today, routinely converted to behaviorist concepts that display the weaknesses that Chomsky pointed out in Skinner's attempt at behaviorist linguistics. So, just as Turing replaces intelligence with behavior that fools people, in deep learning the term rationale, which properly refers to a rationalist logical derivation of a system's response from its internal knowledge, is coerced to mean input that affects the output. Input in the stimulus or input in training data. A hypothesized internal property of cognitive systems, now scientifically well studied in psychology and neuroscience, has been coerced in deep learning so that awareness of X, as when something is called X aware, what it means, the behavior of this system is conditioned on X. Entirely behaviorist, nothing about what we actually know about awareness could be any further from relevant. But now let's return to the founding of AI and consider an early work of John McCarthy, who was credited with giving the field its name in 1956. Unlike Turing, McCarthy's mission was all about looking inside intelligence to see what computations it requires. An issue separating many West Coast theories from the East Pole is whether inference is a kind of logic. McCarthy's East Pole position was certainly yes. One of the earliest AI papers was McCarthy's 1959 paper, Programs with Common Sense, in which he proposed a system he called the advice taker. He gave an analysis of the capabilities required of an intelligent agent, which were to acquire new knowledge by inference, to process abstractions, and to learn by being told. His solution was that knowledge representation must be language-like, must be structured symbolic expressions. This enables abstract encoding symbols, storing immediate consequences, which he called common sense, through logic, assembling such inference long chains, and learning by being told. To illustrate, here's one of the premises he proposed for common sense deduction. What this formula means is this. If the system knows that X is true and knows that it can ultimately make W true whenever X is true by doing Y and then doing Z, and it wants to make W true, then it can infer that it should do Y. McCarthy's work was enormously influential. In AI, the logic school flourished for decades, filling up the journal Artificial Intelligence with a specialized logic for every task. In cognitive science, not so much. As we'll see in next week's episode in cognitive science, connectionist and probabilistic inference dominated. Along with John McCarthy, Alan Newell and Herb Simon were founders of AI in the 1950s, and like McCarthy, their approach took East Pole positions on these issues. The cognitive processes they studied were conscious problem-solving processes, using explicit representations of facts and rules, and explicitly following those rules as interpreted programs. This processing was primarily serial. Together, these properties characterize what you may know as System 2, which Yoshua Bengio has recently been talking quite a bit about, citing like psychologist Danny Kahneman, who actually took these terms from Stanovich and West. System 1 has the opposite properties on these three dimensions, and is characteristic of predominantly intuitive, automatic processes like most visual and language processing. Simon's particular East Pole position evolved into building production system-based general-purpose cognitive architectures. Their huge tome, Human Problem Solving, was a landmark in the field, summarizing 2 decades of work. At this time, AI heavily overlapped with cognitive science. Their work was based on human experimental data, recorded eye movements, and written transcripts of people thinking aloud as they solved problems in symbolic logic, chess, and cryptarithmetic, which had problems like this, where you have to figure out which digit each letter stands for in order for the result to be a valid addition of 6-digit numbers. Their model of human problem solving was heuristic search in problem spaces. Problem spaces were graph structures in which the nodes were knowledge states consisting of about 20 symbols, with operators performing transitions between nodes about every 5 seconds. These operators were production rules. Like McCarthy's rule that we saw, where the left side is a condition, a symbolic pattern containing variables, and the right side is an action to take. The current problem state matches the condition. The knowledge state nodes were symbol structures where each symbol was a pointer to a chunk of symbolic structure stored in memory. There were 3 separate memory systems: long-term memory, short-term memory, and external memory, like paper or a chessboard. Newell and Simon used their human problem-solving data to infer the characteristics of these memory systems. Long-term memory's limitation was a slow write time, about 5 seconds per symbol approximately. Short-term memory's limitation was a very small capacity, about 7 symbols. External memory also had a limited write time. So you can see they were extremely serious about modeling the human mind as a kind of computer. This computer is described here at 3 levels, which the computer vision pioneer David Marr would become very well known for. He emphasized the importance of describing computational systems at 3 levels, especially the highest level, which he, quite confusingly in my opinion, called the computational level. This corresponds here to the knowledge level, which focuses on precisely characterizing the computational problem the system is solving. In subsequent years, Newell and colleagues evolved the SOAR cognitive architecture, which is still used in papers presented at the Cognitive Science Society and has been applied to a very wide range of cognitive tasks. Following in this CMU tradition is one of the most eminent cognitive scientists of all time, John Anderson, whose production system architectures have gone by the name ACT, or Adaptive Control of Thought, ACT. The 2005 version of Anderson's ACT architecture consisted of these 6 modules. In addition to the behavioral psychology evidence supporting ACT, Anderson was looking for neural evidence using functional magnetic resonance imaging, fMRI. The linking hypothesis between the computational model and neural activation was this. The time each module is active, solving a particular problem, predicts fMRI responses, amount of neural activation, in 6 brain regions as a function of the problem difficulty and amount of practice of the subject. Here are some results. Each of the 6 modules of the ACT model were associated with the brain area. The declarative memory was associated with the prefrontal area here. The control state module is associated with the anterior cingulate area here. In these plots, dots are measurements and curves are predictions. I don't know about you, but given the limited number of free parameters available to fit the model for the data, I think this is damn impressive. So that's it for today. Next week's episode will cover several more key dimensions of cognitive theory space and the seminal work of several other prominent authors. This will include a lot of West Coast. So to briefly summarize today's episode, the fundamental question is, what kind of computer is cognition? Symbolic? Neural? There are many dimensions or parameters along which proposed computational models of cognition differ. A coherent set of parameter values based on symbolic computation characterizes the East Pole view. A wide assortment of other values characterize different West Coast views. The East Pole view inherits from the rationalist tradition, in which knowledge derived from experience is regarded as secondary to knowledge that is innate or derived by internal reasoning. Our East Pole linguistics focuses on theories of knowledge, that is, competence, rather than on algorithms for acquiring or using this knowledge. Elsewhere, AI pioneers developed theories of the computational mechanisms for learning and using knowledge, especially of conscious, serial, rule-following cognitive processes. We also talked about problems with some widely accepted positions, including these 3. All knowledge is derived from experience. Behaviorism and the Turing test. Explanation by inner cause. These problems are challenges, some of them for the East and some of them for the West. Episode 2, as I said, will feature more West Coast work. Thank you very much for your long attention, and I'm happy to turn to questions.
That was great.
Thank you.
If anyone has a question, can you raise your hand, click the little hand icon so that we can call on you sort of.
I've also asked, excuse me, sorry. I've also asked Tom to keep an eye on the questions in the chat and curate them. So I also want to give him a chance to pass on any questions from the chat that he thinks would be particularly useful for people to hear about.
Okay.
Yeah, there weren't any questions in the chat, so it's open for
okay.
just raising questions people have.
So are you going to moderate this, Matt? How is this going to work? I see Besnera's hand is up.
Oh, really? It doesn't show that for me. So, okay, Besnera, do you want to go ahead and ask your question?
Well, what are your thoughts about, there seems to be a little bit of like a divisive nature in the types of thoughts, and of course, like maybe this comes from historical reasons, but it has reflected itself also in our community in the sense that perhaps there is no, single answer to these questions. Perhaps humans, when they know how exactly to solve a problem, they have their rules and the algorithm is clear, they follow that algorithm. When they don't, and they have maybe some data, they try to learn from data. And when they don't even have that data or memory capacity to store that data and process that data, they maybe fall into their biases. Do you see any sort of, attempts on unifying these approaches, or?
Yes, so because of the limited amount of time, I am not able to take rich accounts that deal with multiple of these dimensions and assign to various aspects of a problem the values on these dimensions that are appropriate. So lots of people do the kind of thing that you're talking about, ask, for some particular kind of phenomenon, how much knowledge is internally derived, how much is from the experience, and how much, if any, is innate. So for a particular domain of behavior or knowledge, we have to mix all these dimensions together in the right way. So what I try to do in this class is just bring more to awareness what these dimensions are, so that when people are doing these combinations, people can sort of see what's going on better, and see how one mixture of these elements in one theory might relate to a different mixture in a different theory. So it's certainly naive to think that maybe in any case that we look at, it's all A or B in these dichotomies. So I entirely endorse what you're saying, but I also think it's characteristic of work in the field. Does that respond to what you're asking about?
It's a longer discussion, but yeah, thanks.
Thanks, Bezi. Tom, there's a couple questions in the chat. Did you want to do those?
Yeah, I think there were people with their hands raised first, so maybe we should keep going down that list.
Yeah. Why don't you, for some reason, I only see Bezi's hand raised now, so I don't know.
Okay.
Maybe you could,
So
if you're
I think
seeing hands raised.
Yes,
Swadin,
slide from
Yeah.
Paul.
Hi, Paul. Can you hear me?
I can, yes.
Yeah. So one of my questions was, when we talk about innate knowledge, isn't it, even for a child, right? Like, isn't it also acquired by experience in a different generation, maybe? Like even the innate knowledge is kind of a result of experiences, but not by the same the body that we are trying to analyze, but it is coming from a different body that has gone through a different experience, and that's what is the acquired knowledge. So it's still experiences, but just passed on as an initial parameter. So everything is an experience in the end. Like, what do you think about that?
Well, I think that evolutionary psychology tries to connect various aspects of our, for example, the biases that, as Mira mentioned, as well as the innate properties that we have some evidence for. Evolutionary psychology tries to relate those specifically to their function in the course of the evolution of the species, and you can think of that as a learning process. It's like a genetic algorithm at work, learning what then becomes the initial state for later organisms. You can call that learning from experience. I think that's a perfectly reasonable thing to do. I mean, of course, a major part of it is death, so you could call that an experience, not one we definitely are looking forward to. But of course, evolution is all about the characteristics of organisms that allow them to survive and reproduce. So that is a kind of experience, if you like. But in any event, yes, I think that it's not uncommon to think about innate knowledge as the result of some kind of learning process in prior generations.
Cool. Okay. And I had a second thought, which is, do we also think it from a goal perspective? Like if we have a specific goal of identifying a person's face, for example, in a video. Now, from that goal's perspective, we can decide whether, innate knowledge or symbolism is important, or just going through 1,000 videos to detect the face is enough to solve that specific problem. So a goal-oriented view of analyzing these approaches, like, is there any, do you have any thoughts around that?
Well, I mean, I guess to the extent that what you're referring to as a goal here defines a particular task,
yeah,
then certainly there's a lot of discussion of the relationship between the different mechanisms and the tasks that they are crucial for solving. So absolutely the role of inductive learning from lots of data in certain kinds of tasks, maybe facial recognition is certainly discussed, but also there's interest in what kind of innate characteristics of our perceptual system may be at work in how we're actually processing those faces as we experience them.
okay.
Thank you.
Thank you.
Okay, then I think Gonzalo was next, then we can move to the questions in the chat.
Sure. Paul, such a great lecture. Thank you. My question may be silly, but something always bothered me. Maybe you can provide some insight. It always suggests to me that seems that people learn faster than machines. We have these huge machines as big as buildings, but they still take like several orders of magnitude longer to learn than people. Well, why do you think is that?
Well, I think that the story that's, presented from developmental psychology, which is showing how early infants have knowledge of how to organize social events and physical events, suggests that there are innate organizing principles, which means that when the data comes in, it's prepared in a certain way that makes learning much more efficient. So that's the reason that innate knowledge was first proposed by Chomsky, to solve the problem of how with such a small amount of data a child can learn such abstract and rich knowledge systems as our grammars are. So that's the conventional story. Does that speak to what you're asking about, or did I miss the question?
It is an answer, and thank you.
I mean, I don't want to imply that I endorse the view that innate knowledge is the only part or even the main part of the answer to your question. We still certainly know very little about the space of possible unsupervised learning algorithms, and we may just be in the wrong part of the space. And
sometimes I wonder if it is the architecture itself. I mean, are we if we model computers as the models of the brain, but they still learn so differently than the brain? Is that the right architecture or the right model to make? I have more questions than really answers. So, but really a lot to think about.
Absolutely. Thank you.
Okay, so moving to the chat, and I guess going based on likes for the questions, Ben Van Derme asked, as models like GPT-3 march towards being well beyond the footprint of what we'd consider as human-bounded rationality, both in memory, computational cycles, and access to sensory information, i.e. the internet, what is something key about understanding human cognition that might inform AI development? And I'm sure he'd accept multiple things instead of just one thing. And Ben, feel free to pipe in if you wanted to add things or follow up on that.
Did you want anything to that, Ben?
No, that's a good. As always, Tom does an excellent job.
Okay, so I guess we could ask the question about whether the form in which the knowledge that GPT-3 is, the form of the knowledge GPT-3 acquires is a form that allows for maximal flexibility of use and generality of use. So obviously people are looking into this all the time and trying to see to what extent can quickly or even with zero-shot experience do new tasks that hadn't been directly trained. Of course, that's part of the research program, but I think the strong abstractive power and generalization power of rules with variables and symbolic structures in supporting a wide range of general purpose problem solving and computation makes me wonder whether the form that the knowledge that GPT-3 has will make it able to display the kind of combinatorially rich capabilities that symbolic forms of knowledge provide. That's just a question, not an answer. What do you think, Ben?
I'm not sure. It's a good question, and rather than answer, but I guess a succinct version of the question is like how much is our intelligence, and especially the things you spoke to today, sort of governed by the fact that we are bounded computational devices, and as we get the ability to build increasingly infinite computation, like how much will intelligence, like the study of intelligence between AI and humans, actually diverge, or if there just never will be enough compute, and the ability to generalize will continue to be essential for both machines and humans.
I mean, I think you have a very good point that the study of intelligence in GPT-3 versus in humans could very well take rather different forms given the very different constraints under which those different kinds of computation operate, as you say. I think that's true. And I think a number of people at Microsoft and elsewhere are always interested in the question of how to build collaborative systems that take advantage of what is limiting in one system being a strength of the other, so that the fact that they're different is actually a strength and not necessarily a limitation. And in fact, sometimes my view of the current spurt of progress in AI is that the main relation it has to cognitive science is somewhat opposite from what you were asking for. It's not so much from this point of view what cognitive science can teach us about GPT-3. It's what GPT-3 can teach us about cognition, which is that, having had only natural organisms to study the cognition of until now, we've had humans, we've adults, babies, we've had brain damaged and intact individuals, we've had animals, all sorts of different cognizers to study. But now we have a very different cognizer to study as cognitive scientists and to try to understand the theory of. And as you say, there's every reason to think it could be quite different from theories that are appropriate for systems that are working under the constraints of natural cognition. So I think that's a super exciting prospect for cognitive science. And as you know, the kind of work that you do, a lot of people are very excited about doing psycholinguistics on language, on BERT, taking what we've learned in cognitive science about the questions to ask and the methods used to answer them, and taking those and applying them to a very different kind of cognizer. And so that's another important connection between modern AI, which actually gives us some intelligence to work with for the first time, and cognitive science, which I think is every bit as exciting as the other direction of what we learned about human cognition might be able to inform us about what to do in building, in improving GPT-3.
Thank you. That was very well put.
Thanks, Ben.
Okay, so next, Andy Goris asks, how is new technology for scanning working brains, more detailed anatomy of the brain, and experiments in growing brain cells and watching their behavior, how are those things influencing theories of cognition, or are they influencing theories of cognition?
Well, a point in John Anderson's 2005 paper was, if I'm not mistaken, that in order to match well the proposed architecture of his cognitive model and observations in the brain, and this was certainly true, I know for certain that this was true about trying to connect the predictions from his computational system and human behavioral experiments, that the models had to be modified, and the decomposition of the computation into modules had to be reformulated in light of what was learned from looking at behavioral data in problem solving and learning behavior in the laboratory, but also I think in terms of the neural imaging results. I do think that to the extent that that kind of work continues, we are in the business of learning about what kind of deep models of visual processing best fit what we're seeing in neural activation in the human visual system or animal visual systems more often, I think. So I think that we definitely are seeing feedback into the modeling enterprise from the neural data. And I'm sure that that will continue to be more and more important. It has already been quite important in the study of computational models. Maybe that's stretching it a little bit, but somewhat computational models of consciousness have been very heavily shaped by what has been observed about neural components, interactions for different states of awareness and so on. So I think that it's been rapidly growing in importance, that flow of information from neural data into cognitive theory development. Did that address your question? I guess you asked it, Tom.
Yes, thanks.
Okay, yes.
Great. So next was Jenny Chen, who asked, what are your thoughts on spiking neural networks? Do you believe they will generalize well across multiple types and dimensions of data, or are there only certain types of tasks that they'd be advantageous for?
Well, I'm not as much an expert on spiking neural networks as I wish. So my answer is not as informed as I would like, but I would say that the use of spikes as a kind of implementation level feature of neural networks has not struck me yet as sort of fundamentally changing the more high level descriptions of the computations that are going on. So I would want to see evidence of that before concluding that whether neurons spike or not is more than a low-level implementational detail, but something that really profoundly affects the computation at algorithmic and higher levels of description. So maybe you know reason to believe that about spiking models, and if so, then I would like to hear about it and would think that's important.
Yeah, thank you so much. I don't like I like what you said about how spiking neural networks need kind of a larger architecture change, because from what I understand, spiking networks are just kind of swapping out, the plane in a neuron for a function, and so it's not really changing anything. Like it's not changing the structure of the brain on a whole.
Right. I mean, one thing I can mention from my own work is that the work that was done using spiking neurons as a way of binding together variables and values, for example, binding together the agent of some proposition with its role, so that you have, if you have John saw Mary, then you have John bound to the receiver role. And so there were models proposed in which neurons encoding the information about John and neurons that were coordinated with neurons that encoded information about being a perceiver. Their neural oscillations were correlated or synchronized. We showed that kind of use of time to do variable binding was just a particularly temporal implementation of more general mechanisms for doing that variable binding that didn't necessarily involve time. So it might or might not be a useful way of implementing a neural mechanism for binding variables to values, but our work didn't suggest that it was fundamentally different, really, in the computational power that it offered. But that's just one small bit of relevant experience. So thanks for the question.
Thank you.
Okay, so Felix Faltings asks, do you think System 1 versus System 2 thinking follow different models of cognition? Because it seems like neural networks do more System 1 thinking, while symbolic reasoning looks more like System 2 thinking.
Well, I think that this is a good context to remember, the warning we got from Besmira right off the bat, which is basically that there are parallel subconscious components and conscious serial components to very many different cognitive processes. They have to somehow work together to get the job done. So in John Anderson's production system models, you fire one production at a time. It's very sequential, just like Newell and Simon's production system models were. But which production fires is determined by a parallel process of spreading activation through a network. So inside the whole production firing process, there are parallel operations, and those are not accessible to consciousness. So there is always a mixture of these different aspects. And so I think that you could say that certain cognitive processes have more System 1 and others have more System 2 to them. But I think you have to look at it pretty much that way. And I agree with what you said, that the most natural connection is to use neural network processing, which is parallel and not naturally symbolic, to model the System 1 aspects of a cognitive process, and to tie that in somehow with using symbolic structural computation for more System 2 aspects of the computation. That's the huge challenge of doing neurosymbolic computation more generally. But I do think that we're going beyond merely saying, well, we can do certain things called System 1 tasks with neural networks and other things that we use symbolic methods to do with our System 2. We're beyond that for figuring out how to interweave these, because any real task is going to involve a combination of the two.
Okay, and let's end on that note. I think that's a great place to end it. We're out of time for more questions, unfortunately, but I don't know if Paul, if you want to take a look at the questions that were there, or maybe people could just ask next week when Paul's back again to continue his presenting. So let's thank Paul again.
Thank you for your questions and for your attention, and I will do my best to respond to questions.
Great, thanks, Paul. Okay, thank you, everybody.
Thanks, Matt.
Bye.
Bye.